All right, so in this video, we're going to talk about differential equations. I know we've discussed them in the past, so a lot of this stuff initially will be a review. But either way, a differential equation, if you remember, is just an equation that has a derivative in it. And so in this case, we've defined dy dx to equal capital F of xy. This is now a function of multiple variables, both x and y. And when you solve a differential equation, there are two different types of solutions. There's a general solution and a particular solution. The general solution is the one that's still going to have the c's in it. It's going to be a function of x in this particular case, but you'll still have that plus c. And the particular solution can be found when you're given an initial condition. So you've given a point, x naught and y naught. So the easiest example I use a lot of times, not only because it's easy, but because it's very quick, is just your basic dy dx equals 2x, and we'll even use an initial condition here of y of 2 equaling 1. Well, we know that if we move the dx to the other side, that we can go ahead and integrate both sides. On the left, we would have our y of x, and on the right, we have our x squared plus c. So that would be the general solution. The general solution is going to come with a family of curves. We've got our standard parabola when c is equal to 0. When c is equal to 1, we move the parabola up. When c is equal to -1, we move the parabola down, etc., etc. So we have infinitely many solution curves for that given differential equation. Now, if we want to use our initial condition to find the particular solution, we'll go ahead then and plug in the point. So y of 2 would then equal 4 plus c, which is equal to 1, and therefore c equals -3, which means for the particular solution, now we have one and only one curve. It just so happens to be the one that's shifted down 3 units. So there's just a brief review again on differential equations, what a general solution is and what a particular solution is. I'll go ahead and clear the screen, and then we'll take it a little further and interpret these differential equations graphically a little bit more. And then from there, we'll be able to move into numerically approximating solutions of differential equations. All right, so now we're ready to take a look at slope fields. And so I've done most of the work here already on the screen, as you can see. It just made more sense to talk through most of this one. So we're going to consider the example where we have dy dx equals xy. So this is the example differential equation. And if you guys remember, dy dx implies slope. So what I've done here is I've constructed a table. These will be my x values up here, and these will be my y values over here. So when I take these numbers, -2, -1, all the way to 2, same thing here, and I plug the x's and the y's into the differential equation, it spits out these blue numbers. For example, if x is -2 and y is -2, that's going to give me a +4. When x is -1, y is -2, that's going to give me my 2. So all of these numbers are just found in this particular case by plugging them in and multiplying them together. Okay, so these are all of our slopes. Now, the slopes are the slopes of the tangent lines to the curve at the point. And so this is called a slope field, this guy right here. All right. You can see these very, very small line segments, sometimes referred to as lineal elements, denote these slopes. The easiest thing to pick out here is the 0, 0. So you can see zeros all the way up and down, all the way across, right, because of the product. And you can also see the slopes of these lines are 0 all the way through. Now, a couple other things, the corners. A slope of 4 versus a slope of -4. You can see we would have our positively sloped tangent line at 4, right? This is the point 2, 2 at 4. So 2, 2 is out here. And that's going to be positively sloped. And then our negatively sloped 4 would be right here. And the slopes do change. You can see they change all the way through, and the slopes of these small line segments reflect that. Now, this whole method, this whole idea comes about because not all differential equations can be solved using traditional methods or even at all. And so many times we're looking to approximate solution curves. Well, if we know that this is, in fact, the slope field for the given differential equation, this actually, I went ahead and I solved the differential equation in a computer and graphed it. And you can see when I take the actual solution curves for the general solution and then superimpose it on top of our slope field, you can see how it takes shape. So by simply understanding the slope field, we're able then to generalize what the actual solution curve would look like for the given differential equation. Now the book's going to have a couple other examples in there that I would strongly encourage you guys to take a look at. This just happens to be one, but some of them can get to be looking a little more complex, a little messier, but needless to say, we're still just studying slopes. We're just now using those slopes to approximate our solution curves, in which case then we could kind of see how it all relates. All right, so now we're ready to transition into Eulers Method. And this method is specifically designed to numerically approximate solutions to differential equations. And so these are just going to be approximate solutions again, but we'll do so in a numerical way. Now, to get things started, we're going to start with the differential equation, dy dx equals f of xy. The actual solution curve to that differential equation is going to be this black curve here, and this is going to be the numerical approximation that I'm using, okay? Now, to do this, it's actually pretty easy to follow, and it's quite clever. We know that our slope is going to be y1 minus y naught over x1 minus x naught. You can see how I've labeled the points there, x naught, y naught, x1, y1, and so the slope of that small line segment can be found by this guy right here. All right. We also know that our slope is defined as dy dx, which equals f of xy. So what we're going to be able to do now is just make a simple substitution. First thing that I'll do is I'll multiply the x1 minus x naught over here. So I'm going to have the difference in x's multiplied by the slope equaling the difference of y's. So we've got our y1 minus y naught equals the m times x1 minus x naught. And so the y1 minus y naught I'm going to leave alone, but the m, that was our dy dx times x1 minus x naught. And then we also defined our dy over dx as f of xy. Now, I'm just going to change notation here briefly. The y sub 1 is going to equal y naught plus the f of xy. Nothing there different other than adding that over. But the x1 minus x naught, that's going to be the change of x, the delta x. And so I'm going to replace that with the delta x. And so this is a very specific formula for this one particular line segment. If we want to generalize it for all of the line segments, then we're going to go ahead and use n's instead of actual numbers. So if we call that y sub n, then this would be y sub n minus 1. Notice there's a difference of 1 between those things, followed by the f, which is going to be evaluated at x sub n minus 1. The y is going to be evaluated at n minus 1. And then we have our delta x. So this guy right here, this is the general form of Eulers method. And we'll go ahead and take a look at an example then to see exactly how all this works together. Okay, so now we're ready to take a look at an example approximating a solution of a differential equation using Eulers method. And so a few things have been given to us. They give us a starting point, and they give us the delta x and the dx, which are the same thing, as a 1/4. So we're going to count up incrementally by 1/4 units as we move on from one to the next. Now, I'll go ahead and write Eulers method down again, the formula for it, so that we can better see it. But the most important thing that I think in a problem like this is actually putting a table together to stay organized. So the table that I put together might look something like this, where we have an n, an x sub n, and a y sub n. Now we're going to do 3 iterations, the first 3 approximations for this. So our n is going to start at 0, and then we'll have 1, and then we'll have 2. Okay? So when n is 0, then we have x sub 0, which would be the first x value, which would be 0 in this case. And then when n is 0, we have y sub 0, which would be the 1. So that point that you start with is always going to be given. It's much like a recursion formula where you can't find the next one unless you had the previous one. That little bit of information there is really important to get started with. The next thing is that the change of x, right? These are my x's right here. The change of x each time will be by 1/4. So if this is 0 and I increase by a fourth, that's going to be a 0.25. And if I increase by another fourth, that's going to be a 0.5. So what it boils down to is us finding these two things. Okay, we need to find those y values, which makes sense because that's y sub n that we're looking for. And if you'll note, we have a y sub n here equaling all of that. So we've got it solved for the correct thing. Now, we'll go ahead and get started. Since we already have y sub 0, we already have y sub 0, now we're ready for y sub 1. So y sub 1, and you know what, maybe I'll write it like this. Maybe I'll write it as when n is equal to 1, we're going to get y sub 1 equals y sub 0 plus the function evaluated at x sub 0, y sub 0, and then our delta x here at 1/4 or 0.25, whatever you want to call it. Okay, now all I did again was I took my 1 and I plugged it in here. That gives me my 0 there, that gives me my 0 there, my 0 there, and then the 1/4. Now, this says we need to evaluate the function at these two places. So, my y sub 1, I already know is 1. The function then evaluated at this place. So that's going to end up being a 0 minus a 1. So my 0 was my x sub 1 and my y sub 1 was 1. So 0 minus 1 for that guy. And then the delta y again, 0.25 or 1/4, whatever you want to call it. So this ends up being a 0.75 if you run that through a calculator, or you could probably do that one in your head. So there's our first missing piece, 0.75. Okay, so now we'll go down to n equals 2. This will be y sub 2 equals y sub 1 plus f of x sub 1, y sub 1 times 0.25. So again, I went ahead now, and when I plugged my 2 in, there's my 2, there's my 1, and my 1. I'll go ahead a little further now. My y sub 1 was found in the previous step as 0.75. There's my y sub 1, my y sub n, my 1, 0.75. And then we need the function evaluated at this number and this number, x sub 1 and y sub 1. So that's going to end up giving us a 0.25 minus 0.75, followed by the 0.25 at the end. So again, I took my x sub 1 and y sub 1, which would be these guys. I plugged them in here. Here's my 0.25 minus the 0.75. And so when you run those numbers, you end up with 0.625, and that would be the other missing piece that I needed. So just remember, those are points now, the points that we found. These are the points that are along the approximate solution curve for the differential equation. So they're not exact, but they're close. And if we get enough of these, then we could put an approximate curve together and study it as whatever application requires.